Hi, I am Sanjay Patel. Today, in this lecture, we are going to see some subsets of a given ring which also behaves like a ring. Means it has all the conditions what is there in the original ring. And such structures or such subsets of the ring are known as subrings. You have done a similar concept in group theory. Given a group G with respect to some binary operation star, if we have a non-empty subset H of the group G, which also has the same properties as the group G, then such a set H is called a subgroup of the group G. Okay, so let us begin with the similar structure in ring theory also. We have also studied different types of rings and other things in our earlier lectures. Let us begin with a subset of a ring which is itself forms a ring, means satisfies the same 8 conditions of ring. So I start with the definition. Let R plus dot be a ring. R plus dot be a ring and capital S be a non-empty subset. Be a non-empty subset of the ring R. Okay. If the set S itself forms a ring, with respect to the same binary operations, say that addition plus and dot, addition and multiplication of the ring R, then this set S is called a subring, of the ring R. Okay, so given the ring R, we want to study which kind of subsets are there which has all the same conditions or same axioms with respect to the same operations of R in the set S also. And such subsets are very important because instead of studying the whole ring R, if you study only this smaller set S, you can have the same property as the main ring sometimes. So let me tell you that given a ring R with respect to two binary operations, addition and multiplication, if you take a non-empty subset S of the ring R, if you want to prove that S is a subring, then again by definition what we have written here is if S itself forms a ring, means the set S also must satisfy all the 8 conditions or 8 axioms what we have discussed in our first lecture about ring, that S also must satisfy all the 8 axioms of the ring. So it is again the same long task to check even a smaller collection is a ring. But instead of that, before we take any example, let me give a very nice and very helpful result which help us to reduce our work. Instead of checking all the 8 conditions, it is sufficient to check only say 2 conditions, and that we are going to prove as a very important theorem about subring. So this is a basic theorem about subrings, and it says let R plus dot be a ring and capital S is a subset of R and S is non-empty set. Okay, then prove that S is a subring, prove that capital S is a subring of the ring R if and only if, let me write this way, subring of R if and only if S satisfies the following conditions. S satisfies the following conditions, and the conditions are these two. First is that S must be closed with respect to addition, and also additive inverse must exist. That all things we can say in just one condition, that for every A and B belongs to S, we must have A minus B also belongs to S. And secondly, for every A and B, A comma B belongs to S, we must have A into B also belongs to S. Okay. So let us prove this. That is, if and only if means it is a necessary and sufficient condition for a non-empty set S to be a subring. So one part is very simple, and it is this condition this way. Suppose the set S is a subring. So by definition, S itself is a ring with respect to the same binary operation, binary operations, say addition and multiplication, which are defined in R. So we know that S is a ring and it satisfies all the conditions. So in particular S also satisfies these conditions. Therefore, I can say S is also closed with respect to addition and multiplication. Okay, because S is a ring, it means S satisfies all the 8 conditions of ring. So I can say S is also closed with respect to the 2 binary operation. That means for every A and B belongs to S, I can say that A plus B belongs to S. Okay, and all the conditions are satisfied. For every A belongs to S, I can say minus A also belongs to S. And if you combine these two axioms, I can say for every A and B belongs to S, A minus B also belongs to S. Instead of this, you can write here B, so that you can understand directly that for every B belongs to S, I can say its negative belongs to S. So given A and B belongs to S, since minus B also belongs to S, I can combine these two and say A minus B belongs to S. And further, it is also closed with respect to multiplication. So by the axiom number 6 in the definition of ring, I can say for every A, B belongs to S, A into B also belongs to S. So by definition of ring, we have proved both the required condition in this theorem. So this way it is trivial. Now the reverse. For proving the reverse part, what is given is S a non-empty set and satisfying the 2 conditions. So we are given the 2 conditions, 1 and 2, that is for every A and B belongs to S implies A minus B belongs to S, and for every A and B belongs to S, we are given that A dot B belongs to S. And we want to prove that S is a subring. What is to prove? S is a subring. That means I must prove S itself is a ring. S is a ring actually. So we must check all the 8 axioms which we are writing in the definition of ring. So first condition is already there. So let me write this way. So first thing, by 1 I can say it is given already that for every A and B belongs to S, I have A plus B also belongs to S. Okay, that is very obvious because A plus is a binary operation in S, in the ring R also main, and since I can say S is the zero element also belongs to the ring because if I take say this way, if I take A equal to 0, not this way, let me check all the conditions one by one. Since S is subset of R and R has commutativity and associative property, okay, it is clear that plus is commutative and associative in S. That is, I can say A plus B is equal to B plus A, and A plus B plus C is equal to A plus B plus C for all ABC belongs to the set S. Because if ABC or elements belongs to the set S and S is subset of R, so it is also in R. In R we have these properties. Remember, this commutativity, associativity, this kind of properties are known as internal properties of elements. If it is in the main ring or in the main set, it is always true in its any of its subsets. Like set of real numbers. The multiplication of real numbers is commutative. So if we take any subset of the set of real numbers, then in that subset also multiplication is commutative. So this kind of properties, commutativity and associativity, always holds if it is in the main set. Okay. Now what I want to show is the zero element belongs to the set S and negative is also there. We know that we have this thing A plus minus A equal to 0. Okay, A plus minus A equal to 0 for every A belongs to R. For every A belongs to R. Okay, so I can also say that A plus minus A is 0 for every A belongs to S also because S is subset of R. Fine. Now, if I say if A belongs to S and minus A belongs to S, then that implies I can say A plus minus A also belongs to S, and that is 0 belongs to S. 0 belongs to S. So the element 0 exists in the set S. That is S also has the same 0 element as the 0 element of R. Okay. Further, it is clear if I take A belongs to S, then A belongs to R, and this implies minus A also belongs to R. Minus A belongs to R. Now, A plus minus A is equal to 0 for every A belongs to R. Okay, that is known to us. Now, A belongs to R and S has 0 element. I should take not this way. What I should prove here is this way. instead of this condition, let me, here A belongs to S, so A belongs to R, and minus A belongs to R. Okay, that is fine. But since 0 belongs to S, 0 belongs to S, let me take this way. Let me change this. That A belongs to the set S is given. Okay, be any element. And now 0 belongs to S. So therefore, by the first condition, which is given in the hypothesis, I can say that 0 minus A belongs to S. See the condition given. For every xy belongs to S, x minus y belongs to S. So I am putting A equal to 0 and B equal to A. So I will get 0 minus A belongs to S. That is minus A belongs to S. So what I have proved is, for every A belongs to S, there exists minus A belongs to S. And we know that A plus minus A is equal to 0. So that condition, additive inverse exists, is also satisfies. Finally, the next condition, the closure property, is already given for multiplication. We also have, for every AB belongs to S, implies A into B belongs to S. So that is, the set S is closed with respect to multiplication. This is given to us in the hypothesis. And the two properties, associativity and distributivity, both holds, as S is subset of R, and the operation of means associativity for multiplication and distributive property is true in the main ring R. We can also write it is true in the subset S. So it also holds in the set S. That means what we can write is, we have A into B into C is equal to A into B into C is true for all A, B, C belongs to S. And we also have the distributive property, A dot B plus C is equal to A dot B plus A dot C, and B plus C dot A is equal to B dot A plus C dot A. Again, this is also true for all A, B, C belongs to S. Because if we take any elements in S, they are also in R. And in R, both of these conditions are true. And these conditions are internal property of the elements. So this whole discussion says that the set S satisfies all the required conditions, 8 conditions of a ring. So therefore S becomes a ring, or S is a ring. So therefore S is a ring, okay, with respect to the same operation, plus and dot, okay, and therefore I can say S is a subring. S is a subring of the ring R. So we have proved the necessary and sufficient condition for a non-empty set S to be a subring. So now onwards, instead of checking all the 8 conditions, remember, whenever you want to prove that a set S, non-empty set S, this must be non-empty first of all, you must check the given set is non-empty. It is non-empty, it is subset of R. Then you have to check only these 2 conditions. For all AB belongs to S, A minus B belongs to S is true. And for every AB belongs to S, we must have A into B also belongs to S. Then only we can say that S is a subring of the ring R. Okay. Let us take some examples of subrings to understand. And then we'll discuss some results about subrings in our next lecture. So let me take some examples of subrings. The first thing is, let us take the ring of real numbers, say R plus dot be the ring of real numbers, okay, with respect to our usual addition and multiplication of real numbers. Then we know that this Z, if I take S equal to Z as a subset of this R, then S is a subring. S is a subring, rather Z is a subring. That means I did that way. If I take the set Z subset of R, no need to write this here. If you take Z subset of R, then this Z is a subring of the ring of real numbers, because you know it satisfies both the conditions that for every A and B belongs to Z, means if you take any two integers, then A minus B is also an integer. And also, you know, for any two integers A and B, if you multiply them, then the product is also an integer. So it is obvious that S is equal to Z is a subring of the ring R. Another example of subring of this ring R is the set of rational numbers. If I take Q as a set of rational numbers subset of R, then Q is also a subring, of the ring of real numbers, because if you have A and B two rational numbers, then A minus B is also a rational number, and if you have two rational numbers, then the product is also rational. So these are the two examples of subrings of set of real numbers, or the ring of real numbers. But if I consider the set of natural numbers, okay, but the set n of natural numbers, which is also subset of the set of real numbers, this is not a subring, is not a subring of the ring of real numbers, because if I take say, if I take A is equal to 2 and B is equal to 3 belongs to the set n, then A minus B, that is 2 minus 3, is minus 1, which is not in n. So that first condition of the Subring theorem is not satisfied. So this is not a subring of R. So remember, all the subsets of a given ring need not be a subring. Only some subsets which has the same properties or same structure as the original ring is a subring. Okay. Let us take another example of subring. So problem number 2. So consider the ring of complex numbers. Let C plus dot be the ring of complex numbers. Okay, and this plus and dot are the addition and multiplication of complex numbers, which you know very well. Then prove that the Gaussian ring, I mean rather the set Zi, let me write independently, prove that the set Zi defined as A plus I into B, where A and B belongs to Z, is a subring of the ring of complex numbers. So it is very easy. First of all, you note that Zi is non-empty. You can say that this 1 is equal to 1 plus 0i belongs to the set Zi. So I can say that Zi is a non-empty set. Remember, this is our set S. So I am first proving that it is a non-empty set. Now the second thing I should prove is, for every AB belongs to S, A minus B belongs to the set S. The set S is the set Z of I in our example. So let's start with any two elements. Say instead of A and B, I must use some other notation. Let say Z and W belongs to the set S equal to Zi. Okay, so I can take say Z is equal to A plus IB and W is equal to C plus ID. Okay, and where A, B, C, D are obviously integers according to this condition. So what I want to prove is Z minus W. So now if I take Z minus W, then you know how to subtract these complex numbers. We get A minus C plus I times B minus D. This and this both are integers. This belongs to Z and this also belongs to Z. So Z minus W, which is of the form say X plus IY, where X and Y also belongs to Z. So I can say Z minus W is an element of the set Zi, okay, which is S. So what we have proved? For every Z and W belongs to the set Zi, we have Z minus W also belongs to Zi. Okay, this is our result number 2. So we have proved the two things. It is non-empty and it satisfies this condition. What remains is to show only the closure property for multiplication. So again we start with two elements, say Z is equal to A plus IB and W is equal to C plus ID belong to the set S, which is Zi. Then if you find Z into W, then Z into W means A plus IB into C plus ID. This is equal to AC minus BD, you know the multiplication of complex numbers, plus I times AD plus BC. All A, B, C, D here are integers because of definition of this set Zi. So this is also some integer and this is also some integer. So this product Z into W is of the form X plus IY, where X and Y both are integers. So I can conclude that Z into W belongs to the ring, this set Zi. So what is proved is for every Z and W belong to the set Zi implies Z into W also belongs to Zi. That is our result number 3. So from 1, 2 and 3 it follows that this Zi from 1, 2 and 3, 1, 2 and 3, it follows that this Zi is a subring of the ring of complex numbers, So this one should prove subrings. Okay, let us take a different example. I will take an example of subring in the ring of matrices. Say this is my new problem number 3. So let M2 cross 2 set of all 2 cross 2 real matrices with respect to addition and multiplication of matrices as a ring. I am writing like this with the ring of matrices with real entries. Okay. Then determine which of the following subset is a subring of the ring M2 cross 2, okay, of this ring. So let me list some subsets of this. So first of all, I will take S1 is equal to set of all matrices of the form A, B, 0, 0 such that A and B belong to R. Number 2, S2 is equal to, say let me take as A, B, 0, 0, A and B belongs to R. Okay, these examples are very important. So just I am writing all these statements. I will be proving only one of this. Remaining you can take as your exercise. Say A 0 0 0, where A belongs to R. So all matrices of the form A 0 0 0, and fourth, set of all diagonal matrices A 0 0 B, where A and B belongs to R. Okay, and let me take one special problem. S5 is equal to set of all A, B, C, D. This kind of say matrices where this A, B, C, D are let me take some other condition instead of this. I take this way, where AD minus BC, AD minus BC is say not equal to 0. That is, this matrix is non-singular, and ABCD are obviously I am taking as real values, real numbers. Okay, so for this problem, just I am telling you that I am going to prove one or two out of this, and the remaining you can do it on your own. So let me prove, say for example, this one, and I will discuss this problem. So 2 and 5, and so first of all, the second problem here, S2 is set of all matrices of the form A, B, 0, 0, where A and B are real numbers. Okay, so first you have to show that it is a non-empty set. As this matrix 1 2 0 0, this belongs to S2, I can say the S2 is a non-empty set. So this is my result number 1. Next, let us take some two elements A and B. Now since elements of this set are matrices, I will denote it using capital letters. So let capital A be one such matrix, A, B, 0, 0, and another matrix B, I am taking again from S2, say C, D, 0, 0. This both belongs to S2, be any two matrices. So I am taking two arbitrary matrices in S2. And if I now find A minus B, you know it is very obvious. If you subtract these two matrices, what you will get is A minus C, B minus D, 0, 0. Okay, so this is also of the form P, Q, 0, 0, where P I am taking as A minus C and Q I am taking as B minus D, and both of these are real numbers. So A minus B is also a member of S2 because S2 contains this type of matrices. So the conclusion here is, if for every A and B belongs to the set S2, we have A minus B also belongs to S2. This is my result number 2. Finally, what is left is the matrix multiplication. So for the same two matrices A and B, I will be finding A into B also for the same matrices which we have written here. So now if I find for the same A and B, if I find A into B, where A and B are arbitrary matrices as taken above, I want to see what is the multiplication of these two matrices. If you multiply these two matrices, what we are going to get is, you know how to multiplying this row with each of this column. So A into C plus B into 0, so it is 0. Then A into D plus B into 0, so 0. Now this row is 0, so both of these numbers will be 0. 0 into C, 0 into 0. So this is of the form A into C, A into D, 0, 0. And it is of the form, say, P, Q, 0, 0. And therefore I can say this also belongs to S2. So what is proved is, for every A and B belongs to S2 implies A into B belongs to S2. That is, the set S2 is closed with respect to multiplication. So we have proved that S2 is non-empty, number 1. S2 is closed with respect to this addition and additive inverse property. And AB belongs to S2 implies A dot B also belongs to S2. So thus S2 is a subring of the ring M2 cross 2 of real matrices. The subring is also denoted by the same symbol as ring because it is also a ring. And just I'll tell you that all these sets given in this exercise, 1, 2, 3, 4, S1, S2, S3, S4, all are subrings of the ring of matrices. That you can try and give the detailed proof. And now let me discuss this last one, set of all non-singular matrices. So that is problem number 5. Let me choose first problem number 5. S5 is equal to set of all 2 cross 2 matrices such that A into D minus B into C equal to 0. In short, if you take two non-singular matrices, then we must check whether their multiplication and addition is also non-singular. Is it true? See, if you look at this matrices, this kind of matrices, AD minus BC means determinant of this matrix is, it is not equal to 0. I must say it is not equal to 0. Let me change that in this. Yes, it is there. It is not equal to 0. By mistake, I have written here it is equal to 0. So it is set of all non-singular matrices. Suppose if I choose, let me try. Let us take one matrix A is equal to 1, 0, 0, 2. Okay. Then what about this determinant of this matrix? That is A into D minus B into C is 2, which is not equal to 0. So I can say that A belongs to the set S2. Okay. Sorry. It is not S2, it is S5. A belongs to the given set S5. Same way, I would like to take another matrix and try. Say B is equal to 0, 1, 2, 0. And for this, determinant of this matrix is 0 minus 2. So it is also not equal to 0. So I can say that B also belongs to the set S5. So A and B both belong to S5. But now if you find A plus B or A minus B, whatever, then what I will get is 1, 0, 0, 2 plus 0, 1, 2, 0. If you add these two, what you are going to get is 1 plus 0, 0 plus 1 is 1, 2 and 2 here. And clearly, if you find the determinant of this matrix, that is, if you find mod of A plus B, then it is 1 into 2 minus 2 into 1. So it is 2 minus 2 equal to 0. So I can say A plus B is not an element of the set S5. So thus, what I have proved is A and B belongs to S5. A and B belongs to S5. But A minus B does not belong to S5. So S5 is not closed with respect to the operation of addition of matrices. So S5 is not a subring. S5 is not a subring of the ring of matrices. Okay, so this way you can check whether a given set is a subring or not. All these problems are very important. So you just keep in mind, and we'll be discussing again the same problems in our other topics. In the next lecture, I am going to prove some results about subrings and discuss some interesting things about subrings. So till then, goodbye. Thank you so much.